My dear friends, Bhunesh Oza at your perusal again. We have completed generator protection of a large generator of the capacity 120 megawatt, 210 megawatt, 500 megawatt or 660 megawatt. Now we will be talking about large power transformer protection of certain MVA capacity, maybe 100 MVA, 250 MVA, 415 MVA or whatever. Power transformers up to 1200 MVA single unit are available. But we are talking about large power transformers. Distribution transformers, there is no protection. I mean, so to say, there is no comprehensive protection. On primary side, there is diofuse, and on secondary side, there is MCCB. But for these two, there is no special protection. But power transformers have to be protected by the comprehensive scheme of protection. So, in some 5 or 6 sessions of half an hour each, we will see how power transformer is protected. Power transformer is a very important equipment, but its construction is very simple. So usually it is very reliable. And because it is a static device, you see, generator is a rotating device. Induction motor is a rotating device. Transformer is a static device, and therefore it is also totally enclosed. You see, the tank is completely enclosed and oil immersed. Therefore, the faults are rarely developed. But if the fault develops, its consequences are very serious, because fault means flashover, and flashover in oil means oil is inflammable and the transformer can burst. If you have visited substations, you would have seen that if there are 3 transformers or 2 transformers working in parallel, then they construct a wall in between, so that if transformer bursts, it does not damage the nearby devices. Therefore, faults are rare, but if at all faults occur, we should have a comprehensive protection. Therefore, we will study the different types of faults, their consequences, and relevant protective system, so that we understand the protection of power transformer fully. So mainly there are 3 kinds of faults. Faults in auxiliary equipment. These are incipient or minor faults. They do not cause immediate damage to transformer. But in time to come, maybe it may take 1 hour, or it may take 1 day, or it may take 7 days, but it may result into serious fault. So such minor faults are usually sounding alarm. They do not cause trip. Some such minor faults cause trip also, but rarely. Mostly they sound an alarm, so that you come to know that some incipient or minor fault has occurred, and you may attend to that, right? Second kind of fault is external, through faults, not within the transformer, outside the transformer. They have to be taken care separately, because you see, you need not open the transformer. But third kind of faults, the internal faults, you have to do many things. First thing, you will have to disconnect the transformer. Second thing, you will have to remove the wires from the bushings. Third, you will have to remove the bushings. Fourth, you will have to remove the transformer cover. And once you open the cover, the oil is exposed to atmosphere. Therefore, all gases and moisture will enter into that. So oil is useless now. And then you take out the oil, and then you take out the core winding assembly and search for the fault. rectify the fault. Then you put it back, and then you will have to uh, refilter the oil. You have to send the oil to filterization plant and then fit the cover and bushings and everything. It's a time-taking process. Therefore, the the protection which is meant for internal fault should operate for internal faults only and not for external fault. As we have seen in generator, it should not operate for through faults. Through faults, some other protective devices are taking care. So we will see one by one. Today we will be covering only one, that is faults in auxiliary equipment, right? Because I do not want to lengthen any video more than 30 minutes or at the most 40 minutes, because you see people are very busy nowadays, and it's difficult to find time of 1.5 hour to hear the video. Therefore, the faults in auxiliary equipment. These faults are usually minor faults. They do not damage the transformer immediately, right? But if they are allowed to persist, they may develop into serious faults. Therefore, such faults must be detected, sensed, and attended. More importantly, some of these faults are non-electrical. Many of these faults are non-electrical. So electrical relays will not be able to sense these faults. So we will have to have a devices, protective devices, which can sense these non-electrical fault. Right? So that is very important. And therefore, the devices which are used, the protective devices which are used for such faults are very important. You cannot underestimate them. So what are these faults? The first probability is oil leakage. Some hole happens and the oil very slowly, but it is leaking through. So you might be knowing that transformer tank is fully filled, and there is a conservator tank above transformer, and between conservator tank and the transformer tank there is a pipe, and it is leading to conservator tank. Conservator tank is half filled with oil and the upper half is air. And that has to be like that, because if the load increases, the oil level will go up, and if the load decreases, oil level will go down. And when oil level is going down, it is sucking air from atmosphere. Now when it sucks the air, moisture should not be sucked, right? Therefore, you see all uh, transformers with the conservator tank, one pipe is connected, and that pipe at the end, there is a device in which silica gel is filled. Silica gel absorbs the moisture, and it color is usually blue, but when it converts into pink, it is full of moisture now. So you have to remove that silica gel and expose it into atmosphere in heat, so that once again the uh, moisture is uh, evaporated and you can fill up once again. So when the oil level goes down, the air comes through silica gel. So it is moisture free, because moisture reduces the dielectric strength of oil. It is said that about 0.01% of or 0.1% of moisture reduces the dielectric strength to 20%. That means 80% less. That means obviously there will be a serious fault in the transformer. Similarly, in the oil, the gases also should not be there. The air that is filled, the dissolved gases, some gases which are conducting, some gases which are harmful, some gases which make chemical reaction should not be there. Also, the mechanical impurities, because you see when you are drilling and some doing machining of the transformer tank, at that time some mechanical parts are left. So those are to be removed. those mechanical impurities are also required to be removed. So these things are very important when you are commissioning the transformer. So uh, uh, this oil leakage, the oil will slowly leak from the conservator tank, and then it will leak from the main tank. And if the uh, winding is exposed to air, then it is not, I mean, the distance is not meant for air. The dielectric strength of air is 22 kV RMS per centimeter, whereas dielectric strength of oil is about 150 kV per centimeter. So therefore, obviously, if the winding is exposed to air, there will be a flashover and the fault will occur. So oil leakage is not an electrical thing. You see, no electrical relay will be able to sense the oil leakage. For that, you see, we have a Buchholz relay which we are going to see, right? The Buchholz relay is used. It is connected between transformer tank and conservator tank. And at the top of the Buchholz relay, once again, the trapped air is there. If the oil is gasified because of minor fault, then that small gas will go into the Buchholz relay. So oil level in the Buchholz relay will come down and the Buchholz relay will operate, sounding an alarm. This, any case, we are going to see, but oil leakage is sensed by Buchholz relay only. It is not sensed by any electrical relay. So Buchholz relay is a must, very essential in any power transformer, right? It is not there in distribution transformer, but power transformer it is always there. Uh, and also if the oil leaks, the temperature of the winding will increase, right? Conservator tank is provided with an oil level indicator also, having an alarm facility. So if oil level leaks, the oil level will go down and oil level indicator will sound an alarm to let you know that oil is leaking. You can go to the transformer and see where the oil is leaking, and you can take the necessary actions to stop that leakage, right? So oil level indicator in the conservator tank is also a very important protective device. You see, this cannot be done by any electrical relay. So these things one has to remember. So this is the oil leakage, the first abnormality. First small incipient fault. Second incipient fault is deterioration of dielectric strength. You see, oil will slowly, dielectric strength will deteriorate as the time passes. It does happen. However, you take actions, some gases, some moisture will enter, and dielectric strength of oil will decrease. So people are instructed that every month or at every certain interval, there is one small uh, place where from you can take a small sample of oil from transformer and check the dielectric strength. The fresh oil should have the dielectric strength of 200 kV per centimeter. That is 50 kV for 2.5 millimeter. Usually the oil tester sets are, these two spheres are there and they are kept 2.5 millimeter away. Their diameter is 12.5 millimeters. So the uh, the the stress is uniform. Yes, uniform stress distribution is there. 12.5 centimeter diameter spheres and 2.5 millimeter. It should be 50 kV if it is fresh oil, and slowly it will goes. It will decrease, and when it turns out to be 30 kV, then you have to take out the oil and refilter the oil. That means you have to take the transformer for maintenance, refilter the oil and fill it up, right? So if the dielectric strength deteriorates, then the fault will occur, because you see its dielectric strength is less and your distance is based on the fresh or if not fresh, at least 150 kV per centimeter. But if it is less than 120 kV per centimeter or 30 kV for 2.5 millimeter, then uh, it can be hazardous. So before it happens, you see, you should take actions. So that is the second kind of abnormality. Third is failure of ventilation system. Large transformers are always provided with cooling system. Say one 250 MVA transformer is there. It delivers 250 MVA with oil pumps and air fans. That means air cooling and oil pumps, oil cooling. That is, oil is not naturally cooled. Oil is cooled by circulating the oil at high speed with oil pumps. But if oil pumps fail, then its capacity will reduce to some 150 MVA or 165 MVA. And if air fans also fail, then its capacity will reduce to 125 MVA. So, uh, if you want to deliver full power, if you want the transformer to deliver its full MVA, then oil pumps should be running and the oil fans below the uh, transformer tank, the oil fans, fans are there, big fans are there. They are continuously running. But if one fan fails, then the cooling will not be sufficient, right? So in that case, there are two important protective devices. One is oil temperature indicator with alarm and trip facility, and winding temperature indicator with alarm and trip facility. So if oil temperature goes up, the alarm will be sounded. You will come to know that some fan has failed or oil pump has failed. You can take actions, right? And if it is not under your reach, before you reach, the oil has become quite hot, the winding has become quite hot, and it can damage the insulation. You see, then trip also will occur. Oil temperature indicator and winding temperature indicator will provide trip also, if at all things are out of your control. But usually people will reach and take the things into action, because tripping a transformer of 250 MVA means it can damage the, it is hazardous to power system stability also. So that way the protective system of transformer is very, very critical. So, and pump also, there is oil flow indicator. So if oil flow is less, then indicator will also give an alarm letting you know that oil pump is not working properly. So there are many such auxiliary protective facilities which will guide you as to what is the problem, and you can attend to that problem, right? Uh, Another important uh, minor fault is weakening of insulation between laminations. You see, stator core is laminated. Transformer stator core is laminated. 0.4 mm laminations are there, and they are varnished so that one lamination is not in electrical contact with nearby lamination, because otherwise the eddy current losses will be high and transformer will be heated. You see, iron losses should be very low. You see, transformer has the efficiency of the order of 99.9 or 99.8. So losses are hardly 0.1 or 0.2%. So, but if the, because of heat or something, because there is, say, interturn fault may occur, and because of that there is a interturn between two nearby turns. So local heat will be there, and because of that laminations will fail. So eddy current losses will increase. Similarly, all the laminations are punched together by core or bolt, and that core bolt is also insulated by rubber insulation. So if that fails, then all the pores will be, all the laminations will be shorted. So that is hazardous. Therefore, that is also to be taken care. For that, you see, usually winding temperature indicator, oil temperature indicator is there. Over and above that, Usually 3 or 4 RTDs are kept in the transformer at different places, at the top, at the bottom, at the middle. You see, so those RTDs will sense the increase in temperature and will let you know that here the temperature is increasing. Yes, there is something wrong. So you can take actions. So this is improper joints or connections. You see, the while commissioning, joints are not proper, loose joints are there. So there will be heat. So all connections should be very tight and proper. There, the joints are the core bolts, etc., or the bolts at the bushings, etc., are tightened by machines. Machine operated uh, pliers are there, not simple pliers. Personally, one cannot tight so much. So local heating generated by improper joints may slowly lead to deterioration of oil if the joint is oily must particularly. The oil temperature indicator and or winding temperature indicator is there. And if there is a local heat somewhere inside, then that much heat, that much oil will be gasified, and that will go in the Buchholz relay. And Buchholz relay also sound an alarm to let you know that certain things has occurred. Interturn fault. In generator, we are providing interturn fault, but here interturn fault is not that big fault, that's not serious fault. It will generate only local heat. So Buchholz relay for this is enough, right? So these are the different incipient minor faults which are not damaging the transfer immediately. You have got enough of time to attend them. So usually you will attend and rectify them. So one of the important devices is Buchholz relay. Buchholz relay operates an alarm if there is a small incipient fault, but if there is a line to line or something big fault, then it will trip also. So what is the construction of the Buchholz relay? So we will see the figure to see the construction, and with that we'll see the operation also. Buchholz relay is like this. Right? On one side it is coming from oil tank, on the other side it is going to conservator, right? Because it is in between. Tank is on lower level, conservator is at upper level. So oil is coming from tank and going to conservator tank. And Buchholz relay is partially filled with oil. The upper part, 4, is accumulated gas. Now there are 2 floats, as you can see. So number 3 are floats. The float will change its position if its buoyancy changes. That means it's क्या बोलते हैं the uh, the the balance is disturbed, then it will twist. It will change its position. Normal position is this, and you can see that there is mercury. Number 2 is mercury. There are mercury switches. So mercury is there. Mercury is good conductor of electricity. So when some local heating is there, so that much oil will be gasified and it will go to Buchholz relay upper side and the oil level will drop down. So buoyancy will change. Therefore, that alarm circuit will be completed. The float will change its condition, it will twist, and the alarm will be sounded, letting you know that some minor fault has occurred. But if there is a line to line fault or big fault, then oil will be rushing. The gas that is there of the oil will be rushing, and it will be uh, uh, it will thrust on the baffle plate, which is shown number 1, right? Number 1 is a baffle plate. So that changes the buoyancy of float 2 and it will trip the transformer. So Bhupaul's relay can sound an alarm also, and it can trip also. I mean, this is the simple construction of Bhupaul's relay. And this is a must because Bhupaul's relay is the only relay. Winding temperature indicator, oil temperature indicator, RTDs, and the oil level indicator in the conservator tank, they are the devices which can sense non-electrical fault. So these non-electrical faults are very important, right? Because electrical relays, overcurrent relay or anything will not be able to sense this because current is not increasing or decreasing. Nothing is happening to current. So these devices are very important. Bhupaul's relay is a must in every transformer. But there are certain drawbacks also of the Bhupaul's relay. One thing is vibrations and shocks. If some substation is near railway line, in railway line the railway is passing, vibrations occur. So that may operate the mercury switch and unwanted tripping may occur. So that is one drawback. Then another drawback is the minimum time of operation of Bhupaul's relay is about 0.1 second. That is 100 millisecond, 5 cycles. Usually for transformers, nowadays when the fault level is 25,000 MVA or 35,000 MVA, we want the operation within 1 cycle. So they are sluggish. The Bhupaul's relay is sluggish. And Bhupaul's relay is limited to application for minor faults and non-electrical faults. Electrical faults, Bhupaul's relay cannot detect. So I mean, these are the drawbacks of Bhupaul's relay. But otherwise, for non-electrical relay faults, Bhupaul's relay is a must, where we are not concerned about time. 0.1 second is not worry for us. We can wait for minutes together. Certain times we can wait for hours together. Certain faults are so minor that you can wait for hours together for rather rectifying the fault. So that is not a problem, not a big problem. But yet these are the drawbacks. With this, my friend, I end my this session. I told you that I will take only auxiliary faults. Then I will take the external faults in the second session of transformer. So it is very, I've been sending in LinkedIn and I've seen that in LinkedIn, my message that please share my videos, and there are some 5,000 views of that uh, message. That means my message is reaching to people. I again and again request you that my viewers are my ambassadors. One person at least, if he shares to 10% and requests him to go through the whole video, you will get knowledge also, and I will earn the view hours, right? So, and view hours, number of likes, number of views, etc. is very important in social media, and that is for what we are doing this. We want to let the name of Adapt Me shine in the whole world, and we are giving knowledge free of cost. So, I mean, we are not doing anything wrong. So, I would request all the viewers to please view the whole video. Don't just pass through. Don't just like. Don't just say you have liked the video in LinkedIn or Facebook, but go through the video. You will get some knowledge, because so many people have written to me that what you are teaching we have not learned in universities, because the engineering colleges are not teaching these things. Therefore, you will get knowledge also, and I will earn the viewers. So please share to as many friends, as many engineers as you know. Till then, my friends, I thank you for patiently hearing me. and good day. Goodbye.